Okay, so we're going to begin with the definition of a planar graph. And a planar graph, well, there's a very complicated formal mathematical definition, so we're going to go with the easier definition, which is basically you have a connected graph, and it's a connected graph in which you can draw it such that none of the edges cross. So it is planar if it can be drawn in such a way that none of the edges cross. So if you go ahead and you draw a graph and say you have something like this, if you do it like this, okay, firstly that is a planar graph because none of the edges are crossing, and you can add in some more edges here like that and like that, and then just say for example you add in an edge over here. Now on first look you're like, the edges are crossing so it can't be planar, but you can draw it in such a way so that they don't cross. So you could have drawn it something like this, and you could have redrawn it to be, something like that. So it is still planar, and you have to consider that when you're looking at the drawings of whether it is planar or not. So again, another example here would be, again, just taking this piece here, and at the moment, let's just do it like that. So that is your complete graph of order 4, but you can redraw that red edge in such a way that it goes like this. So the complete graph of order 4 is planar. So it's just something to note. As long as you can redraw your connected graph in such a way that none of the edges cross, it is planar. The official formal definition actually refers to things like the embedding of the vertices in the real world square, the real number square plane kind of a situation. You have a function that goes from vertices to that, and there's mappings and everything like that. So we're not going to get into that because you haven't reached the mathematics to deal with it yet. So at the moment, you just have to know it's the connected graph is planar if it can be redrawn in such a way that none of the edges cross. Okay, so one of the things to note about planar graphs is that they have regions or faces. So faces is if you go into the more topological side of mathematics, or surfaces. You may have already done that at school where you looked at faces or certain things. So the idea behind it is, say you have, your planar graph, and we're going to start off like really basic. So the idea behind it is that you will be able to see different regions of it. So you'll have, for example, here an inside region and then an outside region. Will be this entire piece over here. And if we go ahead and look at another example, so the previous one that we looked at had 2 regions, and then now we're going to look at another example here, which is, I'm just going to draw it in quick. And if you go ahead and look at that, you can have a region over here, this whole piece here. You can have a region on the inside of this triangle, and then you have the region on the outside. So this one has 3 regions in total. So 3 regions. And let's look at one more example just in case. And I'm just going to quickly draw it in here. Okay, so at the moment we have a region over here. 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 And we have a region on the outside. So you have 1, 2, 3, 4, 5 regions in this example. And this is going to bring us to a definition about the degree of the regions. So the degree of the regions is, firstly, you have to have let R be a region of the plane or in the plane graph. So we have one of those colored regions basically that we're looking at. Then we're going to be going, okay, the degree of the region is the length of the shortest closed walk. So the degree of R is the length of the shortest closed walk around the region. Okay, so let's do an example of finding the degrees of the region. So let's start off with basic situation. I'm adding this in just so that you can actually see what exactly it entails. So yeah, I'm going to label the vertices so that we can actually discuss what the walk looks like. And firstly, when you look at this, you're going to have, okay, I have a region over here. And then this whole piece, on the outside is a region. And now you're going to look, well, you're going to label them. So you're going to be like, this is going to be region 1, this is going to be region 2, kind of a situation. And then you're going to be like, okay, the degree of region 1. And you're going to look for the shortest closed walk for defining that region. So in that case, if you go there, you can be like, well, I start at B, I go to C, I go to D, and then I go to B again. So that kind of a situation. So you have B, C, D. So you go, okay, what's the length of that walk? The length of that walk is, well, we still need to go back to B. So we have 1, 2, 3. So the degree of that region is 3. Now you're like, okay, now I have to define region 2, and it has to be obviously identified by the closed walk, or the shortest closed walk that entails this region, and you're like, okay, well, how do I do that? So you have to consider, the cases of everything. So you can start at B if you want, B to C to D to B again, but B now has to go to A, and then it has to come back to B because it must be a closed walk. So B, C, D, B, A, B. So the degree of region 2 is equal to, and again, we're going to count the length there is 1, 2, 3, 4, 5, and we have the degree of region 2 is 5. So the whole idea behind this is you look for the length of the shortest closed walk that defines that region. So the hardest one to actually understand is the outer regions, but you'll get the hang of it. So let's do another example. So let's do this one because it's a bit of a challenge kind of a situation. So you have A, B, C, D, E, and F. And we know that there's only one region, it's the outer region for this entire thing. And now we have to look for a closed walk for this region. So the degree of R. So we're going to go, let's start up with A. We go A to B, B to F, and then F to B. Then we're going to go B to C, go C to E, and then E to C, and then we're going to go back to D there. So we have A, B, F, B, C, E, C, D, but then we have to go all the way back, right? Because remember, it's a closed walk. So we have to go from D to C, C to B, B to A. So you have C to D, D to C, sorry, C to B, B to A. Now if we count that, we have 1, 2, 3, 4, 6, 7, 8, 9, 10. So the degree of this region is 10. Okay, so there are some pretty cool things to actually look at when you're doing this, because when you look at this, and say for example you have just this kind of situation, and we have the two regions, what you're going to notice, so let's just go ahead and work out the degrees. So we have R1 and we have R2. So the degree of R1 is something like, you know, B to C to D to E to B. B, C, D, E, B, which gives you your 1, 2, 3, 4. And what you notice in this one here is every single edge gets counted once. But every single edge in this region here is part of a cycle, right? Because you have the red is literally indicating that you're a cycle. So for cycles, the edges get counted once. So then let's just look at the degree of region 2. And let's go from here, we say A to B, then B to C, then C to D, then D to E, and then E to B again, and then we go back again. So we have A, B, C, D, E, B, A. And again, when we go ahead and do the counting of this, we're going to have 1, 2, 3, 4, 5, 6. So the degree of the region 2 is going to be 6. What you can see and what you can notice is that your AB, which is not a part of a cycle, gets counted twice. So edges get counted twice if they aren't a part of a cycle. And this is just going to be a standard situational thing that occurs. And we're going to use this for our next theorem that's coming up.